Hello everyone, welcome to the session on naive-Bayes classification. I am Prasanna. What is naive-Bayes classification and why has it got this name naive-Bayes? Naive-Bayes classification is based on the naive-Bayes probabilistic model. It has got this name because of the assumption that it has got, that is the conditional probability of the features are independent to each other. To explain it clearly, let us look at the example of vehicle data set. The vehicle data set that we are considering here as an example contains 19 lines of record, and the total number of vehicles it would be 19. So each line of record can be mentioned as car, can be described as car or bike. So let's say we know already the number of cars are 8 and number of bikes is 11. So this car, for example, can have the following features such as it can have 4 tires, family can travel, helmet is not needed, seat belt specifications or seat belt necessity, boot of the car, storage capacity, etc. So these are all the different features. So each of this feature will have a conditional probability given given it as family and class label as car. So the condition probability of each of these features are independent of each other. So there is no relationship or correlation between, say, for example, family, seat belt, boot, helmet, four tires, etc. That's why it has got this name naive, because of this naivety. It is highly scalable because the parameters are proportional and linear, and new features, say for example, a new feature in the car, um, say its horsepower range or etc., can also be considered here, and further new features can be easily added to classify it as car. So that's one of the advantages. So I would explain it clearly further. So let's see the formula of naive Bayes, which is the probability of y, that is the class label, given xi features, is equal to prior probability, which is probability of y as class label multiplied by the probability of x features given the class label as y. So we'll have to multiply each of these probabilities. So the posterior probability would be prior probability multiplied by the likelihood, which is the probability of the features given that it is y, divided by the evidence. So this would be ignored, and why it is ignored, we will see it further. So the denominator here, that is the probability of x, is nothing but the sum of the probability of being car and not being car. So the first portion is being car, that is probability of y as car, and probability of x features given that is car. And the second portion is the probability of that it is not car multiplied by the probability of x features given that it is not car. To explain it clearly, yeah, let's take for example, as we seen, car and bike. Number of cars are 8 and 11. Number of bikes is 11. So the probability of that it is car, which is already known prior condition, would be number of cars divided by the total number of vehicles, which is 8 by 19 gives 0.42. This is the prior probability that we have to substitute it here. Then comes also the second portion in the denominator. As we saw, it's not being car, so that would be number of bikes, that would be 0.578, 11 by 19. So you can see, in order to explain it further clearly, let's um, view it as proportions of area. So let's take this square, and the x, this portion would be the y class label, which can be a car or bike, and this would be the x, which is the evidence or features. So you can see here the probability of being car would be 8 by 11, that is the car proportion, and then being bike would be 11 by 19. Yeah, so this is how it is divided, and you can see the sum would be always the constant, so it will not change and will not depend on the class label. So therefore, you can say, after ignoring the denominator, the parameters are going to be linearly proportional and features can be added easily. So let's further look into it. We have in this view, the evidence or the features is not applied yet. So we are just seeing it, the prior probability condition, but after applying the different features, the view is going to be limited because based on the features. So you can have four family, etc. Of course, these are all um, uh, different features, and it will be overlapping as it is conditional probability. And here you can see the evidence or the features of bike, that is probability of X, which is not car. So therefore, the above diagram would be limited. And how we can classify this um, based on a particular problem, say if the description of the vehicle is car or not, how it can be done. So let's further look into with, with the problem probability example. So the number of words that which are contained in this vehicle description data set, 19 lines of record. Okay, it will be, for example, 138 given the condition is type car, for example. And the number of occurrences of the following features in the description. Say we have discussed different features, so the probability of X as 4 given that it is car. So 4 occurs 25 times in this 138 words. So 25 divided by 138, which gives you 0.1811. So that would be the probability condition for this feature. And family feature is occurring 22 times, so 22 by 138 whole number of words. And helmet, of course, seat belt, boot, you can see helmet occurs 2 times, seat belt occurs 30 times, boot occurs 35 times. So considering all these probabilities, and we have to multiply each of them as the conditional probability and with the higher probability to get the probability that it is car given the X features. So multiplying all these numbers, we would end up with the value 9.29 e minus 6. So this is the probability that it is being car given the X features. So now let's take the condition where the probability of Y being bike given the X features. So you can see here helmet has more probability, the others have less probability, less occurrences. So therefore you can see in total multiplying the probability of being bike, that is 11 bikes divided by total number of vehicles, and each of the features are occurring very less. So of course the probability is going to be very less, and therefore you can just classify this as, say, for example, probability of Y given car X features is greater than the probability of Y given bike X features. So we can now classify with this available features for family, helmet, seatbelt, boot, etc. We can classify that the probability of that it is being car is more than the probability of that it is being bike. So that's how the vehicle description can be classified, and this is how naive Bayes can be applied to each of the classification problem. Yeah, thank you. Thank you for listening.